last section in chapter 5, 5.5. This is polynomial and rational inequalities. I'm going to try to do this from examples in the book, because basically what this deals with is you learn the other 4 sections so you'd be able to graph polynomial and rational functions. From the graph is where you're going to do the inequalities. For instance, this first problem tells us to solve let me move in here a little closer, solve the x plus 3 times x minus 1 squared greater than 0. Okay? So what we're going to do is we're going to graph it equal to. So we go through the same process we've done before. We know that we have asymptotes at negative 3 and 1. So here are asymptotes, and so, we have zeros at negative 3 and 1. So you can see that they plotted negative 3, 0, and 1, 0. We know that the overall exponential power, leading degree exponential power, is to the third power. It's going to be positive. So that means the end behavior is down on the left, up on the right. We can see that at minus 3, it's in 1. X plus 3 is raised to the first power. So it passes through. We can see that at 1, it's a second power, which is even, so it goes, touches, and goes up. So from that information, we can get the graph. Now, we go back up and look at that. We want greater than. What the greater than means is that, think of it this way. This right here is y's. So this is saying we want all the y's greater than 0. So if we look at the graph, here is where y equals 0, which is the x-axis. All y's greater than 0 are above it. All y's less than 0 are below it. So the solution for this one is starting at negative 3, going all the way to infinity. Now, the problem is we're going to have to indicate here that this is greater than 0, so we're not going to use negative 3, and we're not going to use 1. So a couple of different ways to write this is we could write it in 2 different intervals. We could write parentheses negative 3, go into parentheses negative 1, then parentheses negative 1, go into parentheses positive infinity. We'd have to have the union sign in between, which is what they've done here. Okay. We could also write it as negative 3 is less than x, which is less than infinity, excluding x cannot equal 1. I mean, that's another way you could write it. Preferably, I'd put it in the interval notation, and there you got your answer. Now, this is solving these problems algebraically. So in terms of this one, we have x to the 4th greater than x. So the first thing we do is we subtract the x over, so we have x to the 4th minus x greater than 0. Then what we're going to do is we're going to factor this. So what we do is we factor out an x. That gives us x3 minus 1, which gives us a difference of cubes. Remember your formula for difference of cubes. It's a minus b, a squared plus ab plus b squared. Your cube root of x cubed is x, which is a. Cube root of 1 is 1, which is b. That's how they got this. Okay. Then what we do is we take and set x equal to 0, so there's one solution. We solve for x minus 1, x minus x equals 1 is another solution. And this one right here, we really have to go through, there's really no real solution for this. Because if we subtract this over, we get a negative 1, and we're looking for all of the y's that are greater than 0, and so therefore there's no solution. And so as a consequence, the way we'd write this in interval form is we'd come from negative infinity to 0. From 0, parentheses, we leave, we go to 1, parentheses, we leave 1 and go to positive infinity. So it's all solutions except for 0 and 1. And this is a rational function. And change to an inequality. You can see that we have x minus 1 over x squared minus 4 greater than or equal to 0. So what we're going to do is we're going to graph x minus 1 over x squared minus 4. So remember, the first thing we have to do is that we need to factor the x squared minus 4. That's the difference of squares. That gives us x minus 2 times x plus 2, which this gives us vertical asymptotes at 2 and negative 2. So here is the vertical asymptote at negative 2. Here's the vertical asymptote at negative 2. If we look at this problem, on our horizontal asymptotes, the leading degree is bigger in the denominator's place than the numerator's place. So that means our horizontal asymptote is y equals 0, which is actually the x-axis coming through here. We can then plug 0 in for x, and we find out that our y-intercept is at 1/4, which is what they've plotted here. We can then solve x minus 1 on the top equal to 0. We get 1, so we have an x-intercept at 1, 0, which is right here. And then again, another thing we do is we plug in something past the asymptote to figure out if the graph is here or here, or if the graph is here and here. Once we get the graph, we're going to do the same thing before. The x-axis, which is y equals 0, is where the cutting line is, so to speak. Anything above it is greater than 0, anything below it is less than 0. So we're looking for greater than or equal to 0. So what happens here is we have nothing in this region, but we have something in this region. Here we're coming from positive infinity, and we're going to 1, 0. So this would be parentheses, positive infinity, comma, bracket 1. Then we jump over here, and we can see that, again, I'm sorry, we're coming from negative infinity, parentheses, negative infinity, to bracket, comma, bracket 1. Okay? Here, in terms of this, we're coming from this negative 2 and going to positive infinity. Because see, right here, this will never cross 0. So it's still a solution. So if you look at the solution here, here's our brackets. Negative 1, in terms of this, negative 2, comma 1, bracket, union, parentheses 2, parentheses infinity. And you know what? I made a mistake. This is coming from negative 2. So this is coming from negative 2 to 1. So it's a parentheses negative 2, comma, bracket 1, union, parentheses 2, going to positive infinity. Disregard what I said before.